All right, it's accidentally stopped the recording. Going to pick this problem right back up where I stopped. When I graphed this, it's giving me a weird point here again. So I don't know why Solver's doing this, but occasionally it doesn't find the right solution, or it gives me a solution that's the trivial solution, only occasionally. But if I just delete that point, then the rest of it still looks smooth. And I kind of know what it's supposed to be going towards. How come it didn't give me my point at 4.7? Let me just copy this one down. Weird. All right, let me try and see if I can just solver that last one. All right, I think what the problem was is I was trying to model something that was above the upper critical solution temperature, which it didn't like. So using trial and error, I guess 378, and I'm not getting exact, well, this is, approximately 0, but this data point is supposed to be the same because it's where the two halves of the curve come together. So if I just change this color to match the other side, then I've got what looks like roughly a smooth curve. Change the color to be both. I've got, looks like a little bit of a weirdness up there, but I think it's because of the data points that I graphed. It's trying to smooth it as much as possible. So how did the model do? Well, if I compare what the model gives me versus what the graph from the textbook shows, I've got the same general shape, but if I look at the magnitude, the experimental data shows that the upper critical solution temperature is about 318, which is, in contrast, I get about 375. So there's a bit of disagreement here, and this is because of a couple reasons. Number one is one parameter, Margules, is symmetric, so you can see that in the shape of the curve, so it's centered at 0.5. And if I look at my values for x1a and x1 beta, they're symmetric, right? So I got the same value for x1a as x2b. So that's what one of the predictions is. The other problem here is that my model for excess enthalpy was seemingly pulled from thin air. So the problem statement told me that my excess molar enthalpy of the mixture is measured to be 5,719 times x1 times x2. Where does that come from? The problem just gives me that. Remember, this is a function of temperature as well. However, if I were to obtain what that functionality was, when I performed this integral, if I actually had this as a function of temperature like it was supposed to, then when I integrated this, it would have been a much more difficult integral to solve. So to improve this model, what I would need to do is obtain a better estimate for the excess molar enthalpy and then perform that integration to get a better functionality for A as a function of T. Now, this is the solution that was given in the example from the textbook problem. This is example 13.5 and 13.6, by the way, in Dom and Visco. I thought of another way that you could potentially do it, and I'm going to give it a try. I'm not totally sure if this is going to work here, but I'm going to try it anyway. And the way that I'll try it is we've already figured out how to get the alpha value for 300 Kelvin, but we have all this other data here too. So if we can figure out a better functionality for A, in other words, if we can calculate A at all the temperatures given on this graph, maybe we can recreate this graph using those values of A. So I need to set up my Excel spreadsheet to be able to calculate this A a little bit faster. All right, so I'm going to rearrange this Excel sheet and I'm going to do it such that I can pull more data from the graph. So I want to rearranging here, and I'm showing you this just because I want you to be able to see what I'm doing as opposed to me just doing it off camera and then showing it to you later. I keep things in a logical order. So x1 alpha, x2 alpha. Actually, I want to bring x1 beta next to it, right? Because I want to read these off the graph and then have the other two calculated by equation. 1 minus b6, that's what I want. x2a is 1 minus a6. That is also what I want. I'm going to have a column for best fit alpha. This is going to be something that I goal seek for. And I am going to want to move my component 1 equation up there, my component 2 equation there. So I'm arraying this such that I can do a table. So what I'm going to want to do is take data off of the chart, and then I'm going to copy everything else down. This can go away now. And my sum has to stay, right? So just making sure that everything stayed the same in terms of references when I move stuff. My sum is the sum of my component 1, component 2 equations. My component 1 is still referencing what I want it to. So my component 1 equation, where did it go? It's in here somewhere. There it is. Component 1 equation should be x1 alpha. So A6 is x1 alpha times exponent of E6, which is best fit alpha. Best fit A times C6 x2 alpha. Okay, that equation is good. And this equation, let's see, C6 x2 alpha is also good. All right, so we get rid of that again. All right, next I am going to just take some data points. So I only had the one data point that we've done. So we've done 0.13 at 300 Kelvin and 0.82. I'm going to want to take some more data points. So this is going to require some reading of the graph. And of course, there's going to be some inaccuracy in translating this from a graph over to numbers. But let's take this data point there. Let's say that's about 0.8. And I'm going to have to redo all this solver anyway, so I'm just going to take these two cells, put them down there. Okay, so 0.08 is, again, this data point, and the corresponding data point for that temperature, whatever temperature that happens to be. Actually, I'm going to need temperature as well, right? Because what I'm going to do is I'm going to plot A as a function of temperature. So I'm going to move everything over by 1 and then delete at 300 Kelvin and add temperature. So at a temperature of 291 Kelvin, I got 0.8 and 0.85. Whoops. Oh, this was 0.08. I think I said 0.8 before. 0.08 and 0.85. All right, at 295, I don't have an actual data point there. And notice I'm not doing every single data point either. That's probably overkill. Although I probably want to do more rather than less. So let's do 292. And let's take the data point there. And I don't have a corresponding data point. It's always best to take actual data points instead of interpolating. See, I'm trying to look at wherever I have a diamond. I don't want to take a data point off the line because remember, the line is just the thing that connects them to visualize better. The actual diamonds are the experimental data points. Let's see, 290. We don't have good data there. I'm just going to do 295, and then we'll do some more data up here. So 295, I've got 0.1. And 0.84. Yeah, see, it's kind of a guessing game to try and get any kind of accuracy. And in general, you don't want to go out to 3 digits of accuracy because you really don't have that resolution of the plot. If I only have tick marks of 0.1, I really don't want to estimate beyond 100th because there's no way I could possibly know. So I'm just going to look at like a rough percentage of the distance I am between 0.8 and 0.9 and estimate like that. So let's keep going. Let's do one for 297, let's say, and we'll do this little diamond there. We'll say that's 0.11, and over on the other side is 0.84, no, 0.83. Yep, because it's a little bit to the left of the last one that we did. This one is our data for 300, which you've already done. Let's do 302. And at 302, I've got 0.13. No, 0.14, we'll call it. I'm kind of doing something I'm not supposed to be doing. I'm not, looking at this with respect to what it should be. I know that it's got to be greater than the one that I did before, so that's how I'm saying it's 0.14 instead of 0.13. Again, whenever you're reading data off of a graph, can expect a decent amount of error. Something we'll talk a lot about next semester in SEPs too. There's a lot of reading stuff off of graphs in that class as well. We'll do 304. And we'll say this is 0.15 and 0.8. Let's do 306. And the X1A for 306 is 0.17. And corresponding is 0.79. Let's do 310. And we'll get 0.2 and 0.76. Going a little bit faster now because I think you get the idea. 312, 0.23, and drawing over 0.74, 0.73. And I hope this works. I'm not 100% certain that it will work. 315, 0.25, 0.26. I'm splitting hairs here. Really just trying to get a good estimate. 0.26 and 0.7. All right, and we're getting up close to the upper critical solution temperature, so I'm going to want some more data points in here. 316. And going to need to be precise as much as possible here. 316, we'll say 0.28 and 0.7 again. I'll say 0.68. And let's do one or two more. 317 and 318. For 317, I'll say it's 0.31. And 0.67. 318, we'll say it's 0.33. And for 318, I'll say it's corresponding to 0.65. All right, so a lot of error is to be expected here, but my hope is that this is going to be better than just pulling this function out of thin air and using that. So I'm going to copy everything down, straight down, by double-clicking that value, and I'm referencing cells that I shouldn't be, it seems like. Why is that? Oh, because I drag stuff down, so I want to reference these. Same thing for for 1. Okay. Whoops, I'm going to need to reference all the correct cells. All right, let's try that. Let's copy that all the way down. All right, that looks much better. Just do a couple spot checks, making sure everything is where it's supposed to be. On every line, I want to reference cells from that same line. All right, so now I'm going to use solver and find the best fit A for each temperature. So solver, and zoom out a little bit. I'm zoomed in way too much. So click on that cell to set it up. Oh, I got solver set up from the last time. So set this value to minimum by changing variable cells in the A column, and subject to the constraints that no constraint to change. All right, delete that one, add a constraint that all these must be equal to 0 as well. Wonder if it's going to like that or not. I should want to minimize this one as well. Anyway, let's see what happens. Solver couldn't find a feasible solution, so it couldn't find them all to be equal to 0, but it got close enough. All right, let's see. I like what solver's doing. Maybe I might try to solve them individually. See, I think the problem is that you can't set a constraint to minimize everything. You can't set the constraint to be a minimum. right? So I'm setting I6, which is my sum, to be minimized by changing these variable cells there, subject to the constraint that these all have to be 0. And solver can't set them equal to exactly 0, but it also can't minimize them as well. So I'm going to try and solver these individually. I'll pause the video for this. Okay, that was only slightly tedious, but I did end up getting it to work. So again, the only thing I had to do was I did them individually. So for the first one, for example, my solver was to set my objective cell of I8, let's see, I did 18 last. So it's this cell by changing the variable cell of the best fit A. And then I just solved them all one by one individually. So I just did it, whatever it was, 10 times. Now, if I want to double check how my best fit A is comparing to my A from before, let's try and pick okay, for 300 Kelvin, I know that my best fit A is the same. Why is it, this is odd, why does it say 2.68? Oh, because I'm referencing, I changed that reference. So I need to reference that cell when I'm going down here. All right, so let's pick 310. 2.267 versus 2.399. So that might be part of the reason for the error. So in order to get a better functionality for A, what I'm going to do is I'm going to plot A as a function of t, and then use that function that I fit. So I'm going to insert a chart, the scatter plot, and select data, edit series values to t. All right, so this is now going to be A as a function of t, A on the y-axis, t on the x-axis. And I want to insert a trend line. And instead of modeling it however I did, looks pretty good linear. Maybe I can just have a linear trend line. Let's see, it's probably not recommended to do this because we know again what the functionality should be. It should have it should go as 1 over t does. But maybe let's try this. Let's just try, instead of this equation, I'm going to try equals minus 0.0224 times t plus 9.211. All right, copy that all the way down. Now I've got different A's, so I'm going to have different, I'm going to have to redo solver. So data, solver set my objective cell equation 1 equal to a value of 0 by changing variable cells, all of these, and subject to the constraints that all of these cells are going to be equal to 0, and also these equations are going to be equal to 0. Okay, solve it. All right, and because I had such a large temperature range from before, it got a little bit broken at this higher temperature. So I am going to not plot all these. I'm only going to plot up to 315 on both sides. And that's looking to be much better, right? So again, if I look at comparing what my model predicts versus the experimental data, now I've got the magnitude right. One other thing also to note is that I don't have any experimental data for below 290, but the model doesn't necessarily know that. So if this stops, it should keep going, by the way. It shouldn't just stop there. But that's, again, I'm extrapolating after that. I really only want to fit up until what I know. In order to get this top of the curve filled in, I would have to guess at what the upper critical solution temperature is. So instead of 320 there, I'm going to say +1. And then I'm just going to go up to 319. And copy down, copy down. And I'm just going to get rid of all this stuff. All right, so I'm going to expand this. I need to hit solver again, by the way. And it's probably not going to like it if I go a little bit above what it predicts it should be. Okay, solver. Set it up to solve. Delete that one point. Oh, it's giving me the trivial solution again. Let's see. Let's try and give it a better initial guess. And why did I get zeros? Oh, because I didn't change solver again. All right, hit solver. Changing the variable cells. These subject to the constraints. I want to truncate this now. Only up to cell 32. All right, solve it. And okay, that looks much better. It's not getting me all the way there. All right, I probably have to do a few more, but this way actually worked out a lot better than I was expecting, and a lot better than the first way that the textbook had. So the textbook just, again, pulls this function out of nowhere. It says that it got it from literature. But because this is a function of temperature itself, that is why we have such disagreement in the first method. So this was, again, an example of how to model liquid-liquid equilibrium, how to get the phase equilibrium curve from some experimental data and then model it with the Margules model. You can also do phi-phi models. So we talked about those for vapor-liquid equilibrium, where you model both phases as non-ideal liquid mixtures, as real liquid mixtures. Because you do have two liquid phases here, you could also do phi-phi modeling for liquid-liquid equilibrium. We are not going to do that, however. We are going to first talk about a simplification you can make in liquid-liquid equilibrium, and then we'll go on to vapor-liquid equilibrium. So that'll be the subjects of the next couple of videos.